Okay, in this video we're going to look at some financial mathematics, namely simple interest, and I think more importantly compound interest. So simple interest, we'll just gain an understanding of that with a pretty simple example here. We're being asked how much simple interest, $20,000, will accrue at 6% per annum after 3 years. So accrue is just a fancy word for earn. So how much interest is this investment of $20,000 going to earn if we are going to earn 6% per annum? And of course, annum you might recognize, kind of sounds like annual. Yes, it just means per year. So simple interest is what makes simple interest simple is there's no change in our investment until the very end of the term of the investment. So essentially we're going to start this investment with $20,000, right? And then interest is going to accrue on that investment, and at the very end of 3 years we'll get our interest added on. So we'll just have let's just say plus interest. Probably should say total interest. Okay, so we have to figure out the total interest, and there's nothing too miraculous here. We just have to understand that if I have $20,000, the amount of interest I'm going to earn is 6%, of course in decimal form, each and every year, right? So let's just say each year. And there's no change in that $20,000 until the 3 years are up. And of course, that's not how investments work in the real world, but hey, this is a starting point at least. So $20,000 times 0.06, got to be 12 something. It's going to actually be 1,200. Check with your calc. But that'll be $1,200. So we're going to earn $1,200 each and every year. So of course, if we times that by 3, we're going to get $3,600 in total interest. $3,600 in total interest. Now we'll get, I guess, that deposited into our account or a check in the mail, and our final investment now is going to be worth $23,600. So that's how simple interest works. And of course, we have some fancy terminology to learn. The amount of simple interest, I probably should also say simple interest here as well, but most people just use interest, is the amount of our investment, which is actually called principal, and it's multiplied by our rate, our interest rate. Let's just say rate. And of course, it's going to be multiplied by the number of years as well. So we get this nice compact little formula. We usually see a capital I, which represents simple interest, is going to be the principal, the amount that you have invested, multiplied by the annual rate, multiplied by the number of years. And I probably should include that as well, because there's one important thing you got to keep in mind when you're working with interest, is that how your rate is defined has to agree with the amount of time that you're investing it. And all that means here is we have an annual rate. So if I'm multiplying this by 3, and we can look at how this formula kind of streamlines this process, we want to make sure that the time involved actually matches the rate. So just notice we could do this calculation maybe a little more simply by saying $20,000, which is our principal or our investment, multiplied by 6% per annum, or our annual percentage rate, multiplied by 3. And of course, you can see that's just going to produce our 1,200 again times 3. That is $3,600, precisely what we got before. And just keep in mind, in order to get the future value, that's probably the most common terminology, the future value of our investment here is going to be equal to the original principal plus our interest, which in this case, or in this example, like we've done before, is going to be $20,000 plus this $3,600. And I guess I can scroll down to finish it, but of course we have the answer sitting there in front of us. The future value of our simple interest investment here, just strictly using our formulas and getting used to the symbols and the terminology, would give us $23,600 yet again, as before. Okay, so after our short simple interest introduction, now let's have a look at compound interest. And you can see the link there to a spreadsheet that can bypass some of the grunt work involved. But it's important to look at some of that arithmetic that's involved so we actually understand what's happening when we eventually start to wield our compound interest formula a little bit later in this video. So let's get the terminology handled, I guess, first, or dealt with first. We're being told that a $20,000 investment earns 6% per annum, and now we are told it's being compounded annually. Determine the value of this investment after 3 years. So of course the numbers are all the same, and it's nice just to know that if it was just simple interest and there was a stagnant or a constant investment amount for the whole duration of the 3 years, we would end up with $3,600 in interest. If the interest is being compounded annually, as you can probably tell from the table here, after every single year, which of course is what annually is referring to, after every single year we get the interest added on our investment. So our $20,000 is stagnant for the first year, and then there's a balance change every single year. So compounded annually tells you that you're going to have an investment or a balance change every single year. So let's of course look at it. And down below here, just to make note before I forget, that this middle column calculation we're doing here, of course, is just our simple interest calculation that we saw earlier in the video. So the first row is exactly the same, simple interest. We have our $20,000 investment, so $20,000, and we're going to multiply that by our annual rate of 6%. And then I would say to myself, well, how long is this? How many years is this $20,000 going to accrue interest? And of course, if it's compounded annually, it's 1 entire year. And of course, here multiplying by 1's not doing anything, so all this gives us is our $1,200 interest, like we saw before. So our closing balance now after year 1 is going to be $20,000 now increased by $1,200. So note the balance change. So our balance is now $21,200. And so we carry that forward into year number 2. And each of these rows is sometimes referred to as the interest period. Here our interest period is 1 year. So note the balance change, and this is the difference between compound interest and simple interest. Now we're going to earn 6% again, but now it's on a little bit more money than during the first interest period. I guess I can put some dollar signs on the money there. So now we're going to earn 6% on $21,200. It's still for an entire year, and it doesn't change things much, but of course it is changing our amount of interest that we're gaining here. We're now up to, of course I did these calculations before, so we don't have to be watching me switching back and forth between the calculator and bumbling around. But notice now we've earned $1,272 in interest during the second year of the second interest period. And if you're asking yourself, hey, where did that $72 come from? Well, of course, we gain 6%, not just on our original investment or our principal, we gain 6% on the interest as well. So compound interest is quite often referred to as interest on top of interest. So now when I add $1,272 onto $21,200, we're now up to $22,472 and no cents. So we just carry this process forward 1 more year. So now our opening balance at the beginning of the third and final interest period, or year number 3, since the interest period is a year in this first example, first compound interest example, we're now going to earn 6% on $22,472. And note, I'm still taking a second here to say, how long is this accruing interest for? Yes, 1 year. And note the agreement, annual interest, number of years, and our simple interest calculation. And note we should see a slightly bigger interest amount, not just $1,272 anymore, but now we're up to $1,348. And I'm just going to round to the nearest penny. Not going to worry about that too much right now. Nearest penny is good enough. And then our final closing balance is not $23,600, it's a little bit more. It's $23,820 and 32 cents. So we gained a little bit more money, and that's because we're not just earning 6% on $20,000, we're earning 6% for 2 years on the $1,200. And for 1 year on the additional 1272, I better be careful what I say so I don't misspeak. Let's just make it simpler for me and you. We're just earning interest on top of interest, and that's what's given us an extra, what, $220. Not a significant change, but mathematically it is a change. Okay, so the next step in our study of compound interest here is to see if we can bypass the spreadsheet approach that we used in the previous example. Because as you can probably imagine, if our investment lasted for 10 years or 12 years or even 30 years, you don't want to have to do 30 separate calculations. And of course, in this next stage of our study here, we're going to try to find a way to bypass all of that and try to use some magic of our current topic, of course, some exponential functions here to bypass this whole process. So what does that mean? Well, just keep in mind, at the end of row 1, we knew we earned, of course, in the box here is the amount of interest that we earned, and that was $1,200. So we ended up with $21,200 at the end of the first year, or at the end of the first row in our spreadsheet. And you can probably notice that $20,000 is involved twice here in this sum. This is our original investment at the beginning of that interest period, and it shows up here again. So what we can do is just actually pull that out as a common factor in this sum. So notice I could say that that sum is the same as multiplication. And you might not really see any advantage to that, but there's a way of bypassing this whole process by using repeated multiplication. And yes, that sounds like an exponent in disguise. Of course it is. So if we pull out a $20,000 from our principal, and I guess you could say that that is one principal, right? 20,000 times 1. That reminds us to make sure we put a 1 in front of our addition symbol here. And if I pull 20,000 out as a common factor, we're going to be left with our 6% times 1 year. And I guess I'll switch that to a decimal because, of course, you need to use decimals when you're working with financial math calculations and not just the percent symbol. So basically what I'm saying is that if I type this into my calc, we're going to get the same thing. So notice this streamlines the process. So we've removed addition. Now, of course, it's still hiding in brackets, but note another way of looking at this is there's a $20,000 being multiplied by 1 plus a single 0.06, which of course is a multiplier with an extra decimal for some reason. There we go. We can look at this as just multiplying 20 grand by a 1.06. And if you check that on your calculator, it's a lot smoother, and now we don't have to have a couple of columns in a spreadsheet. We can just say, okay, if I multiply by 1.06, I'm looking after this compounded annually business at an annual percentage rate of 6%. Now we have to keep in mind how many times we need to do this, and that's where this interest period and interest period rate stuff comes into effect. But let's just back burner that for a couple of more seconds. Just keep in mind we have to do this calculation 3 times in total. So the next step here would be to take our $21,000, I guess I better say $21,200, and we're going to increase this again by 1.06. Right? And that's the same thing as saying 21,200 plus 21,200 times 6% per year times 1 year. And if you check this one out, that of course will reproduce the second row in our spreadsheet, and we'll be now up to 22,472. And that's, I guess we can number these. This is interest period number 1, or row number 1. This is interest period, or row number 2. And of course, we got one more left. And we'll just repeat this one last time. 22,472, and the final interest period will, yes, be increased by 6. And if we multiply it by that 1.06, we'll get our final balance, which I forgot what it is, but it is here in front of me. It's $23,820, and yes, 32 cents as well. So another way of doing this calculation, check this out. Notice I'm multiplying my original principal by 1.06, not just once, not just twice, but 3 times. So we can spare ourselves a spreadsheet, and we can spare ourselves these 3 separate calculations by saying, if I can get a working pen here again, 20,000 multiplied by 1 decimal 0.06, which remember is our increase each interest period, and that has to be multiplied 3 times. And I think I actually might write it out just so we're 100% clear. I'll spare you the color changes. That 0.6 is constant every single interest period. I think we can now see, oh yeah, that's repeated multiplications 3 different times representing the 3 interest periods. So if you go to your calc and you type in 20,000 multiplied by 1.06 to the power of 3, you will get in one step $23,820, I guess $23,820.32, and we've really streamlined that whole process. It's just simply going to be our principal multiplied by 1 decimal, and just to remind you and finish off this terminology above, that 0.6, which I forgot to color code the second time, of course is our interest period rate, right? Or of course we better be using the decimal form of that in our calculations. Please keep that in mind, although it's still usually listed as a percent in the wording and terminology. And that 3 that's up here in our exponent, of course, corresponds to the number of calculations that we have to do, and that's called the number of interest periods that we have. A single balance change every year over 3 years, of course, is 3 interest periods requiring an exponent of 3. And now I think you can see the connection between exponential functions, because now we have an exponent. So compound interest can be calculated, I guess that's not plural, compound interest can be calculated using an exponential function instead of a spreadsheet. Okay, so now that we see how we can avoid a spreadsheet, you might be wondering why there's one in front of you again, but just to gain some insight into the process so that you can appreciate what the shortcut is doing in a few more moments. So again, we've just changed the compounding here. So what I want you to understand in addition to the wording is that when we speed up the compounding, and not just waiting an entire year before we change our balance, and compounded semi-annually, since semi means a half, we're going to get a balance change every half of a year. So that changes our calculation a little bit. Obviously, it doesn't change it drastically, but there's just one thing we got to keep in mind here, and I think the best way to see it, of course, is still in a spreadsheet. But remember, our whole goal is to try to break free from the shackles and I guess the tedium of calculating this by hand. But we're only going to do the first 2 interest periods. And since each interest period now is a half of a year, as of course the title is saying there, we'll actually figure out what our balance is at the end of year 1 by completing the first 2 rows. So it starts off very familiar, right? We still have our $20,000 opening balance. It's going to accrue 6% interest for an entire year. But here's where we got to be aware. We can't just put 1 here, because of course that's an entire year, and we're only earning interest for a half of a year. So we got to put 1/2. And now for the first time you might understand this, I guess, correspondence between these 2 numbers that you have to be aware of, or I should say agreement between these 2 numbers. If this is an annual percentage rate, which it always will be, the time that you're attaching to your simple interest calculation here in the middle column, of course, has to refer to the number of years as well. And a common mistake is to kind of stick, I'll just undo this in a second, but put a 6 in here and meaning 6 months. And that doesn't work because, of course, this is not a monthly rate, that's an annual rate. So if you do that, you'll accidentally give yourself 6 years interest, and you're only supposed to be giving yourself 6 months interest. So let's undo all of that slowly here. So if you do that calculation, and again, of course, I worked that out in advance to speed things up a little bit, we end up with $20,000. What is it? 6 and 600. I guess that makes sense. That's exactly half of our $1,200. All right, and sorry, that's $600 interest. I'm kind of getting ahead of myself there. Our interest is $600, which of course is half of $1,200. And yes, the closing balance will be $20,600. Now, if you say to yourself, hey, this is a worse deal, we should have $21,200 at least, but remember, this is only after a half of a year. This is our first interest period of 6 months, and once we calculate 2 interest periods, we'll be able to compare a year 1 with the 2 different compoundings here. So we carry this 20,600 through yet again, finish off year 1 here at least. 20,600 gets multiplied by 6% only for a half of a year, because our compounding is a half of a year. And that bumps that up a little bit to 618. And since we've increased the compounding, you can see that we've earned a little bit more interest. It's $21,218. And I guess I don't need to put the decimal of 00 on there. We'll go to the nearest cent, and if there's none, just leave it off. So we get an extra $18, which of course is not life-changing. It's not like you can retire early or anything or earlier, but it just shows you that when you shorten up the compounding, you increase the number of interest periods, and you actually increase up into a certain point at least, but you can increase the amount of interest that you earn on an investment. Okay, so let's see how we can bypass, I guess, calculating all of those rows in the previous spreadsheet. And I guess the answer was our future value of our investment is close to 24,000. Was it 23,880 some dollars? So let's see how we can bypass that. And of course, it's very, very similar to what we did earlier with the compounded annually, except of course now if it's compounded semi-annually, we got an extra half in here. I'm still going to factor out the 20,000, which remember is still our principal, out of that sum. So we'll end up with a 1 plus, and I guess in blue here, we'll have a 6%. I guess we'll switch that to decimal in case we forget, because if you don't switch it to decimal, you'll have 600%. That's a little bit different. And then something nice happens here, which actually makes our life kind of easy, if not predictable, with the formula. This is our multiplier, right? And of course, that half is being multiplied by our annual rate. So what we could do is say to ourselves, well, that's just actually could be written this way. I'm not really changing anything. I'm just going to put that 2 on the bottom. And then we can start to say that that 2 that's on the bottom here, this is the number of balance changes, right? We can call them balance changes. It's kind of slang, but as long as you understand what I'm talking about, that's going to be the number of balance changes each year, or per year. Of course, and that usually gets a variable. It's usually assigned n in most textbooks. Let's not worry about the letters right now, though. I think I will just strike that from the page. But if you figure out that you have 2 balance changes every year, of course, note where that 2 comes from. It's just the annual percentage rate times by a half of a year, but it's usually written this way in our compound interest formulas as a further simplification of this process. And now I got to say to myself, how many times am I going to have to increase by now what we have is an interest period rate of half of 6, which of course is 3%. So note that number that's in here, 0.06 divided by 2, is of course now a 3%. So our interest period rate is 3%. It's usually called that. Right? But of course, remember, when we're working with the numbers, you got to use the decimal form. This is 3%, but that's per half a year or per 6 months. Right? But let's just call it interest period rate. And if there's every half of a year, we got to do a calculation. Of course, that's 2 a year, so we got to be aware that the number of interest periods we have, I guess to color code that yet again, is going to be 2 calculations for every year. And since there's 3 years, we need to make sure we repeat this calculation 6 times. So there it is. And I mean, you can streamline this further if you would like to get to your calculator, but I usually just let the calculator deal with it, so there's no rounding error. But I think we can skip this step, call that 0.03. You could see that you have a multiplier in here now of 1.03, and since the number of interest periods are 6, you got to do 2 calculations every single year. You got to repeat this multiplication 6 times, and let's have a look at that on our calculator here. If we go 20,000, and I'm just going to type it in exactly how I see it. Now, if you want to let the calculator do that for you, you could just type in 1 plus 0.06 divided by 2, but this should make sense. And raise that to the power of 6. We can bypass 6 different calculations in our spreadsheet And if you, I guess I'm going to have to get this off the screen. And if you want to jump back to the previous spreadsheet, you will see this in the very, very final cell. So what is it? $23,881, and to the nearest penny, 5 cents. Okay, so the common confusion always comes from this, the terminology in red and blue here. To keep in mind that if your annual rate's 6%, and if you're going to start doing a balance change every half of a year, you actually can think of it as creating an interest period, or let's just say a half of a year interest period of 3%. And that's just a simple result of our multiplying our annual rate by the number of years, remember. So you're going to have that 2 showing up in the denominator here, corresponding to the compounding semi-annually. And notice I actually kind of tucked it away here, but that 2 is also hiding in our number of interest periods here as well. So if we're chopping our annual rate into 2 equal pieces, keep in mind that's also doubling the number of interest periods. So I think we're getting pretty close. I think now we're going to look at the compound interest formula and do 2 more examples where we keep increasing our compounding. Okay, so here it is, our compound interest formula, and it's a little overwhelming at first, but look at the key structural piece here, of course, is the brackets of our principal being multiplied by a 1 plus something number over and over and over again, specifically n times t. So let's try to connect all these letters to our previous example where n was equal to 2 because we were being compounded, or I shouldn't say we were being compounded. Our investment was being compounded twice a year, so semi-annually. You just got to get used to attaching the compounding terminology to a specific n value. All right, so if you read compounded semi-annually, you say, okay, n is 2. Now let's keep all the other things. Our rate, remember before, was 6%. That's your annual percentage rate. And make sure, by all means, you use the decimal form of that in your calculations. We kind of discussed the n equals 2 thing, so the number of interest periods per year or number of balance changes per year, if it's semi-annually, n is 2, just to see how this all kind of falls into place here. T is pretty straightforward, that's always years. Notice years will correspond to your annual percentage rate if we use our previous information. Oops, except that's not n anymore. We would say t equals 3 years. And of course, if we're investing our 20 grand again, this is just how all these pieces fit together. So note the exponent is the number of interest periods, of course, which is nt, which is going to be twice a year. We got to do a calculation for 3 years in total. That gives us our 6. And that mysterious interest period rate, this is our 6-month or semi-annual rate of interest, has shrunk down now to 0.06 divided by 2, which is 3% or 0.03. So just to show you how those pieces fit together, I don't think I probably have to write this all out again, but it might be helpful. And you can always bypass this with your arrow keys. Remember, if you got this under control, you would say, hey, my principal is 20 grand. I'm going to set up my 1 plus stuff here using my compound interest formula. And I'm going to be aware that my annual rate is 6%, and I'm going to chop that up into 2 equal amounts over that whole year, which corresponds to our semi-annual rate. So we're getting a 3% increase 6 different times, and note the 2 actually shows up in the exponent and also underneath your annual percentage rate. So of course 2 times 3, most people would be better off just putting a 6 in your exponent there. And that is exactly the same calculation as before, of course. So get used to this, and I think I would probably recommend that you focus on what that n is all about, because if you understand the number of interest periods a year and then or number of balance changes a year, you'll see that that shrinks down your rate, your percentage, and also, of course, is increasing the number of calculations or interest periods that you have to do. Okay, so home stretch, folks. We'll do 2 more examples where we'll look at 2 more pretty common compounding periods. Okay, so 2 more examples, and the first one here, of course, we're reusing our $20,000 principal, or our 6% APR, or annual percentage rate, and we're sticking with 3 years for the term of our investment. And now we're going to increase the compounding to 12 times a year. we're going to do a balance change every month or 12 times a year. So right out of the gate here, the most important thing I think to keep in mind is that we're going to have to do 12 calculations every single year. So let's not immediately jump to the formula. Let's just, I guess we could say, future value. And honestly, I kind of prefer to use FV because it's pretty clear that that's future value. But sometimes people think there's two letters multiplied there, and that's kind of needless confusion. But if you want to use FV and PV to represent your future value and present value, you can go for that as well, and you will see that in some texts. But for now, let's not use any letters. Let's just use the numbers again. So we got a $20,000 investment. So 20,000, we're going to be multiplying that by 1 plus our annual percentage rate of 6%. That will change at some point, but just not in this video. And then I'm going to be multiplying that repeatedly, but before we do that, to say, okay, n is 12. So I'm going to chop this up into 12 pieces, which I guess would be 0.5% we're going to gain in our investment every single month. But that balance change, of course, is the most important thing to be aware. So that means up in my power, we're going to have 12 multiplied by 3. So if you look at the spreadsheet at the link that I provided at the very beginning of this video, you can see the spreadsheet for this. And of course, there will be 36 different rows in that spreadsheet, or 36 different calculations. Now you can leave it like that and type that into your calculator to get the future value of your investment. But just to show you that if you see it simplified a little bit, you could do that. It doesn't matter, but I think it's nice to kind of look at this multiplier here. 6/12, of course, is 0.5, so that's 0.5 percentage point. So I probably should double check this on my calc. So 0.5% will show up as that teeny tiny 1.005, and of course that power is now 36. And we can see that, yes, this is an exponential function. That 20,000 is like our vertical stretch number. Our 1.005 is our base, and of course that's the exponent is usually the thing that's changing. That's usually where there's an x or something. But we're kind of a long ways away from x and y at this point. So just be aware, what I do want you to be aware of is that 1.05 is not much bigger than 1, but it's very significant that it's bigger than 1. Because remember, if it's bigger than 1, we're going to see exponential growth in our investment, even if it's teeny tiny. Okay, so but if it's slightly less than 1, then that's of course the reflection of that, which is exponential decay. So we don't want to see any exponential decay in our investment. Of course, we want to see this upward trend, which we will see as long as the base, that multiplier, that 1 plus r over n multiplier, is always going to be bigger than 1. And if it's not, then you pretty much have messed up something, either in your input, in your calc, or your writing. And speaking of input in the calc, let's have a look at this and double check, of course, my decimal representation there. So we can go 0.06 divided by 12 to make sure that is correct. And we can type this in as 20,000. I better get the zeros in there. As 20,000 multiplied by 1.005. And I kind of cringe when I see people typing it in this way. I'll show you that you don't have to worry about messing up your decimal or data entry, or I guess typing in wrong numbers, if you let the calculator do the work for you, simply inputting the top line here. So I might as well show you that at least once. So there is 20,000, and I can just say, calc, can you do 1 plus 0.06 divided by 12 for me? And of course it will. And then I have a nice luxury with my calculator here that once I hit the exponent button, it's clear everything that's in that box is going to be in my exponent. So of course, just put 36 in there to be instead of a multiplication, because a lot of times on most scientific calculators, an extra set of brackets is required up there in that exponent if you don't have that fancy little box template. So please be aware of that. And there we go, and I don't have to worry about screwing up the decimal representation of 0.5%. The calculator can do it for you. So there it is. I guess we can write this down in its entirety here to finish this one off. We're now with a compounded monthly which is somewhere in front of me here. Here it is. It's 23,000. Of course, it was on the calc, but that's long gone now, at least out of my eyes. So $23,933.61, and there we are. Our formula has allowed us to bypass 36 different calculations. Okay, and our last example here, and I think we saved the best for last because we're now looking at compounded daily compounding. Of course, this is the compounding of choice by financial institutions, especially when they are lending you money, because hopefully, as you've seen throughout the video, and if you haven't, you can either go back or just probably look at the spreadsheet and the link that I provided, and you will see if as the compounding increases, so does the amount of our future value. And of course, the growth is slowing down a little bit, and we'll see in a future video that you can increase compounding to like thousands of times a year, but you're not going to see much different in your investment. But a very naive way of looking at compound interest, which is a good place to start. We'll just keep in mind that we would expect that if we increase compounding, that we'll increase the amount of interest that we're going to earn in our investment. But I think it's also good to be not too naive and be aware that that's only up until a certain point. And we'll deal with that in a future video. So let's finish this off. And in the last video, notice I didn't even write the formula down. So you can write that down if it's helpful to you, as long as you understand the structure of the formula. Make sure your R's and N's look a bit different. Okay, so I'm still, and it's hard probably to mess this up because we've been using the same principle and the same rate over and over and over again. So if we have a $20,000 investment, that's our principal. We still have a 1 plus, of course, in our formula, and our annual percentage rate is still 6%. Now here's where most people would probably use 365. Assuming my pen will cooperate, there we go. Most people would probably say, hey, there's 365 days in a year, and of course that is true, and over the span of 3 years, that's probably going to be accurate enough. But keep in mind, if we get beyond a 4-year period, we might want to start considering leap years. So, and we'll look at this on the calculator. You could stick a 0.25 on your 365 as well, but I'd only probably do that when you're dealing with a longer term of an investment, because you're not going to hit too many leap years. Of course, over the span of 3 years, you might not hit any. It depends on the calendar. And most importantly, let's, I guess, maybe color code this. That 365 shows up in our exponent as well. We're going to multiply that by 3. So this is a horrendous calculation. Even with the spreadsheet, if you check it out, there's thousands of rows just to get this to work. And of course, it's kind of a nonsense approach to it. But if you want to go through the spreadsheet, be my guest. But be aware conceptually that we're now shrinking our annual rate down to this teeny tiny daily rate. I guess I can make that in blue. And banks and financial institutions love to advertise daily rates because, as you can see, a daily interest rate in this case is 6% divided by 365. It's going to have a lot of zeros in the beginning of that percentage, and it almost seems like you're getting money for free. But of course, it's just a sneaky way of hiding that 6% annual rate from you. And since we shrink the rate down to a teeny tiny daily rate, keep in mind this is going to be the number of days over the course of a 3-year period. So let's get to our calc and type this in, and we are done. So 20,000, and I think I'll let the calc, of course, do all the work for me. So 0.06 after our 1 plus there, divided by 365, and I think I'll just go 0.00 just to set me up. I'm going to just adjust that. I guess I got 3 zeros in there, so that matters. I'm going to stick on that extra 0.25 in another second. So here's where a lot of you will have to use brackets on your exponent, assuming you want to get the correct answer. You want to make sure that you got 365 times 3 up in your exponent. So notice we got a little bit more money than last time. It's roughly another $10, and that's just because of the compounding and I guess the contract of our investment. And I guess we can write that down in a second, but let's just do a quick comparison. If we did include a leap year, it's probably not too shocking that over the 3-year period, you're only going to get another 0.75 of a day, right? So how does that affect? Oh, and I forgot to leave space up here. So we got to change that exponent to 365.25 times 3. Is it going to change anything drastically? No. You have to go out to the fourth decimal place to see any difference at all. So rounding to the nearest penny, I guess that's good news. And it should make sense that if we only have a 3-year term of our investment, worrying about leap years is kind of silly. But if you want to always include the 0.25, of course, I will mark either or correct. So what's our final answer here? It's 23,943. So this is kind of annoying, our future value. I have to bear with me here, wrap this up. 23,943. I'm flying blind here again. And 99 cents. We'll always go to the nearest penny. So that's going to be the future value of our investment. And you might have the impression that if we keep increasing the compounding and shrinking, the amount of the interest period, that we're going to keep getting more and more and more and more money. And if you want to play around with your calculator, and I will do it once for you, you can actually see that reusing this and of course bumping this to like whatever fits in here. Let's just go with 1,000. What if I have 1,000 different balance changes every single year? Whatever the actual term for that is, it's not very common, so you don't have to worry about it as long as I don't have any rogue numbers here. So if I actually increase the number of interest periods a year to an n equals 1,000, how does that change anything? Well, we're only getting another, another penny roughly, another dollar or so. Actually, it's like 22 cents if you want to subtract those. So you can start to see that if we keep increasing the compounding and shortening up the interest period, we're not always going to see a huge change in our balance. And if I go from 1,000 calculations a year to 2,000 calculations a year, we're starting to see very little difference here as well now, like about a 7-cent difference. So there is a kind of a speed limit on compounding, and I think we will deal with that in a future video. Okay, as I'm trying to wrap up this video, but I thought I would just do a quick little add-on here, just showing you some common interest rates, just to make sure you know what n is in each situation. Of course, here's our 6% here. And we looked at if it's a semi-annual rate, our n is equal to 2. Of course, there's 2 calculations for every single year. We looked at a monthly one. Of course, that one's pretty straightforward, 12 months in a year. And notice now, one way to visualize this is our 6% is chopped up into these 12 itty-bitty little 0.5%. Now, we didn't look at quarterly, but you can probably use your imagination that that's quartering your annual rate into, in this case, if the annual rate is 6%, into 4 1.5s, and that n value would be 4 in your compound interest formula. I didn't include it because the graphic wouldn't be worth too much if you had 365 or 365.25, I guess, divisions of 6%. That's a teeny tiny daily rate. So if you do get a credit card statement in the mail and somebody says, hey, come bank with us because our interest rate is not that high, it's only, and they would probably use the 0.25 to make it even smaller, it's only 0.016% in small print daily interest rate. Right, so it almost seems like you're getting free money, but remember, if you multiply that daily rate by 365.25, you realize it's actually a 6% annual percentage rate. So those are the standard compounding, periods that you will, or interest periods, and common, compounding that you will see in all of your practice problems.